You ever wish the world just came with a user's guide? A manual that explained what everything is made of and how it all works? Well, in a way, it does. That guide is called chemistry, and it unlocks the secrets of pretty much everything, from the phone in your hand to the most distant stars. So today, let's flip open to Chapter 1.
All right, so let's start with a bit of a riddle. What could a simple glass of water, the air you're breathing right now, and the stars in the night sky, what could they possibly have in common? I mean, they seem about as different as you can get, right? But believe it or not, they are all connected by one single fundamental idea.
And the answer is, they're all made of matter. Everything you can see, touch, or even feel is made of this stuff. And the science that tells the incredible story of that matter, what it is, how it behaves, and how it can totally transform, well, that's chemistry.
Okay, so for the official definition, chemistry is the study of the composition of matter. Basically, what's in it. It looks at its properties, what it's like, and it explores its interactions, so how different types of matter get along or don't. It really is the central science, the bridge that connects the physics of tiny atoms to the biology of life itself.
So how in the world do chemists even begin to tackle a subject this huge? Well, they use this really powerful way of thinking. They learn to look at the world through 3 different lenses, or domains, all at the same time. Let's go back to that glass of ice water, the stuff you can actually see and feel. The cold glass, the solid ice cubes clinking around, that's the macroscopic domain. It's our everyday world. But if you could zoom in like billions of times, you'd enter the microscopic domain. You'd see individual water molecules zipping around. And this special shorthand we use to describe all this, that little formula H2O, that belongs to the symbolic domain. To really get chemistry, you've got to learn to see all 3 at once.
Okay, so let's grab that microscopic lens and zoom way, way in. If all this matter is the house we live in, what are the bricks? What are the actual fundamental building blocks that everything is made of? First, the official rule. Matter is simply anything that occupies space and has mass. It's a fancy way of saying if you can put it in a container and that container gets heavier, well, it's matter. It's pretty much all the stuff in the universe.
And the smallest possible piece of that stuff you can have is the atom. Think of it like the basic unit of identity. A single atom of gold is the absolute smallest thing that is still, without a doubt, gold. If you break it down any further, it's just not gold anymore.
But here's the cool part. Atoms are really social. They almost never hang out alone. They link up, they bond with other atoms to form molecules. A molecule is just a team of 2 or more atoms that are chemically stuck together, like the 2 hydrogen atoms and 1 oxygen atom that team up to become a single water molecule, H2O. Now, the way these atoms and molecules organize themselves is what gives us the 3 main states of matter: solid, liquid, and gas. In a solid, like our ice, the molecules are all locked into a neat, rigid structure. In a liquid, they have enough freedom to kind of slide past one another, which is why water takes the shape of its glass. And as a gas, they're just flying free, expanding to fill whatever space you give them. So now we can actually start sorting all the matter in the universe. And the first big question you ask is this a pure substance or a mixture? A pure substance, like pure water, is made of only one type of thing. A mixture, on the other hand, like salt water, has multiple things just physically jumbled up together, not chemically connected. And if you've got a pure substance, you can ask one more question to narrow it down. Is it an element or a compound? An element, like a chunk of pure iron, is made of only one type of atom, but a compound, like our water, is made of 2 or more different types of atoms that are chemically bonded together. You can't just strain the hydrogen out of water. You need a full-on chemical reaction to break those bonds apart. Okay, so we've got ways to classify matter, but how do we tell one type from another? I mean, how do we know gold isn't iron? We do it by looking at their properties, the unique characteristics that act like a fingerprint for every single substance. And there's a really important split here. A physical property, like color or melting point, is something you can observe without changing what the substance is. When ice melts, it's still H2O, right? It just looks different. But a chemical property, like flammability, describes its potential to become something totally new. When wood burns, it's not wood anymore. It has chemically changed into ash, smoke, and gas. We can also sort these properties by asking a simple question. Does it matter how much of the stuff you have? An extensive property, like mass or volume, totally depends on the amount.
A whole swimming pool obviously has more volume than one drop of water, but an intensive property, like temperature, doesn't care about the amount. That pool and that single drop can be the exact same temperature. To study all of these properties, chemists have to measure them. And this brings us right back to that third domain we talked about, the symbolic one. This whole domain is built on a foundation of precise, careful measurement. You could say it's the official language of chemistry.
And to make sure that scientists all over the world are speaking the same language, they use a standardized system called SI units. Length is always in meters, mass in kilograms, and so on. This way there's no confusion, and a discovery in one lab can be understood and tested in any other lab on the planet.
And here is that symbolic language in action. Density is a super useful intensive property. It's the relationship between two extensive properties, mass and volume. This little equation is incredibly powerful because a pure substance will always have the same density, which makes it a fantastic tool for identifying an unknown material. Now, whenever we measure something in science, we are aiming for two things, accuracy and precision. Think of it like throwing darts. Accuracy is how close you get to the bullseye, the true, correct value. Precision is how consistent you are, getting all your darts to land in the exact same spot, even if that spot isn't the bullseye. A good scientist, of course, is always trying to get both. So, okay, we've got the building blocks, we've got their properties, and we have the language of measurement. But how do we put it all together? How does a chemist actually use these tools to go from just a simple question to a huge, world-changing discovery?
Well, the tool for that journey is the scientific method, but it's really not some rigid, boring checklist. As this quote gets at, it's more like a path of discovery. It's a way of thinking and exploring that guides us from just noticing something interesting to deeply understanding how nature really works. And that path almost always starts with a simple observation that makes you go, why did that happen? From there, you form a hypothesis, which is really just an educated, testable guess. Then comes the fun part. You design experiments to really try and prove your guess wrong. If your idea survives all that testing again and again, it can eventually grow into a comprehensive theory, a powerful, well-supported explanation for a whole part of our universe.
So there you have it, our whirlwind tour. From seeing the world on 3 different levels to understanding the atoms that build it, all the way to the scientific process that reveals its secrets. Chemistry isn't just another subject in school. It's like the fundamental operating system for the entire universe, connecting the tiniest particles to the most massive galaxies.
And I'll leave you with this one last thought. Your body, right now, is made of about 7 billion atoms, all working together in this incredibly complex chemical dance. So now that you know some of the basics, it's kind of like having the user manual for yourself and for the entire universe. The only question left is, what are you going to do with them?